This is CS 402 on Wednesday, June 18th, 2014.
Warm up. All right, let's get this started. Warm up 2. Hello. We're starting. Okay. Warm up 2 is due this Thursday, and again, the usual reminder not to copy from it and try to work with your kernel partners. The grading guideline is the only way we will grade, and we can only grade on grading account, and make sure you verify your submission. The kernel assignment, as I mentioned last time, has been posted. I assume that everyone has Ubuntu 12.04 installed. You should try out some basic stuff, make sure it works. And if you still have issues, you should come to see me now. And if you still have issues over this weekend, next Monday, Tuesday, Wednesday, you should definitely come to see us during office hours to get things going. So you should download Unix to make sure they can run it, and then start running some of the basic installation stuff. There's a bunch of stuff you need to install, so follow the installation procedure and make sure it sort of looks like what the kernel spec says it's supposed to look like. Let me know as soon as there are problems. Read the documentation and the spec. Right, the spec is the the web page. The documentation is the PDF, the 70-something page, PDF file. Just read the sort of the beginning part. You don't have to read the entire thing. The kernel assignment, summer is short. We only, we're going to do it in 2 weeks, but I'm hoping that you don't have other classes that you're taking. So this is pretty intense. So make sure you, at least try to start, start it early so you can finish this as soon as possible. Kernel 1 is actually not that difficult. Conceptually, it's weird, so you sort of need to spend a lot of time thinking about it to make sure you get it right, okay? And then, kernel 2, kernel 3 depends on kernel 1. So if you do kernel 1 wrong, it's gonna, you're gonna end up spending a lot of time trying to fix it later on. So it's sort of important to get the concept correct, okay? If you have questions starting with kernel, post them to the class Google group, send private email to me. I'm the most, the person who's most familiar with the kernel assignment. You can send your question to the TAs or whatever, but they are not as familiar with the kernel project as me. Okay, so I would suggest you send it to me. Okay, you can go there to see office hour for the TAs, but the main thing that they can help you with is how to debug, how to use the system, and things like that. Okay, things that are specific to the kernel. Please look at me and the class Google group as your primary resource. Okay, again, you can send it to them, but they might end up forwarding stuff to me if they're not sure. I will record an extra lecture this afternoon, to make up for the final exam on the last day of class. It's meant as a continuation of today's lecture, and it will assume that you have watched this extra lecture before next Monday's lecture. And today's extra lecture, I'm planning to start with an overview of the kernel assignment. There's a lecture slide that says kernel projects or something like that. So I'll start with that. I will also talk about dynamic memory allocation. Okay, so that's the memory allocator, malloc and free, both in the user space and also in kernel space. They actually use different kinds of memory allocator. And also, I will go briefly over, the booting stuff. The booting stuff is not, not that important, but you should know how operating system booting works. But again, that's sort of really not part of the operating system per se, because it's more related to the hardware and stuff like that. So we just have a brief introduction on, booting. The kernel group forming deadline is this Saturday, end of Saturday. So please follow the rule. Every team member must send me a separate email. Okay, so don't send it to the TA. Send me a separate email indicating the names and email address of your partners. And this email must be CC to all your partners. Okay, because otherwise I won't say this is approved. You have to do it again. And here's sort of a shortcut, right? One person can send it to me and everybody in your team, and then everybody just reply to it and confirm that this information is correct. Okay, that's a really fast way to do it. Okay, and also you should notice that if you start doing this and your partner is not doing what he or she promised to do, maybe that's the partner that you should watch out for. Because this person might not keep his or her promises. All right. After this Saturday, anyone who doesn't belong to a team will be grouped together at random to form teams. Okay, depends on how many students are left. You can choose to do the kernel assignment by yourself, so you don't really have to be in a team. But if you end up to have no teammates, this is the rule that was spelled out since the first day of classes. So please don't complain because you have plenty of time to do this, or you can choose to do it yourself. Okay. Certainly, it's possible to do the entire project, the kernel assignment by yourself. You just have to work really, really hard, and it's been done before, so it's not a problem. All right. Okay, so we are still in a race to section 5.2 of the textbook, right? So we're still in chapter 4. Hopefully today we can finish chapter 4 and start on chapter 5. And next Monday, I'll definitely finish, section 5.2, at least to the point where there's enough stuff for you to complete the kernel 1 assignment. Okay, kernel 1 assignment, you should be able to do kernel 1 assignment, and most of it, when I finish section 5.1 of the textbook. So there's a little bit of 5.2 that you need in order for you to finish the entire kernel 1 assignment. Okay, the kernel 1 assignment in the end, you have to, switch on a flag, and that will cause a little bit of trouble, but that's section 5.2 of the textbook. Okay, and we should be able to cover that by next Monday. All right, so we're in chapter 4, talking about operating system design, very high-level introduction to what actually goes into the kernel. And last time we sort of talked about this. How do you quickly start another process? Right? We have this picture. That says, well, here is the parent process, here the child process. When you fork off a child process, instead of copying the entire address space, all you have to do is to copy the page table. Okay, and last time we mentioned that on a 32-bit machine, on Intel machine, right, a page is about 4 kilobytes long, and there's 1 million pages, right? So the number of entries here in a page table potentially is 1 million. Okay, so this operation, when you create a child process, you just copy the page table from the parent to the child. This will make them share all the pages. Okay, so certainly that works for code pages, but it's really not suitable for data pages. Okay, because those things you want to read and write, you can't really share, read and write, global variables. Okay, so copying 1 megabyte, right? Each one of these things, these entry might be 4 bytes, 8 bytes, or something like that. Or maybe 16 bytes or something like that. All right. So let's say that every one of these things is 16 bytes long. Okay. So 1 million entry, that's 16 million bytes that you have to copy. Is that a big deal? It's quite a lot, right? But it's better than 4 gigabytes. Okay. So it's much better than 4 gigabytes. 60 million is really not ideal. So later on, when we look at chapter 7, we're going to see how this is really done. So that so conceptually, you need to copy 1 million entries. Okay, but then we can cut it down a little more. All right? Okay, so now we're going to sort of pretend that, when you start the child process, you're just going to copy the entire page table. Okay? And then you have to fix, all these things with the data entries. Okay? So this particular process is called, so a little bit more of saving. For the text region, okay, when you map, when you copy the page table, so this is like if these files that corresponding to the executable, if you want to execute these files, you have to bring those pages from disk into memory, right? So if this is your file, prog, okay, over here there's text, data, BSS, and stuff like that, okay? You copy them into your memory, okay? So you copy this thing into the, into pages all over memory, okay? And then you have this page table to point to these pages, okay? So this entire process, is sort of considered, it's like mapping the file into memory. Okay, so over here, we have these data sitting on disk. This is the disk, right? You have these things sitting on it. Okay, in order for you to execute code, you have to bring the disk pages into memory. Okay, and then, you have these page table to point to these pages. Okay, so it is like you are mapping this, so conceptually, it's like you're mapping this file into memory so you can access these files directly. Okay, for the code segment, when you try to access them directly, well, you can just read them off as if you're executing them straight from the file. Okay, so that's the idea over here of mapping a file into the address space, okay, as if you're accessing the file directly. But of course, you can't do that because the CPU can't really talk to the disk directly. The CPU can only access memory or talking devices on the bus. Okay, so this is another sort of abstraction that was created. Okay, so all the text region over here, you can also do this trick. Okay, but the data region is a little tricky, right? Because, the program will modify it. So even though in the beginning, you try to map them onto memory, but as soon as you start modifying them, well, then, you really can't, once you start modifying these data, then you got to be a little more careful. Okay, because when you have the child process also trying to modify the same piece of data as the parent process, then they're going to run into each other's, way. Okay, so you got to do something slightly different. Okay, so, we can't really share a data segment, right? So what is the right thing to do? Okay, so what is the right thing to do, over here is that, when we first bring in this page, right, this page corresponding to data, and in our example, also correspond to BSS, okay? When you bring this data from disk, okay, in the beginning, this page looks exactly like what's on the disk. All right, so it's okay to use it, to point to it. All right. So what we need to do is that whenever we try to write to it for the first time, maybe we need to do something slightly different. Okay. So when you try to, let's say that we have, the parent process try to modify, global variables. Okay. It tried to write. So over here, there's a variable say d is equal to 5. Okay. In the data segment, right? So over here, when you bring into the memory page, over here, you're going to have a variable d equal to 5. Okay, this guy is going to say d equal to 7 in one of the instructions in the program. We'll change this guy into 7. If you change this guy into 7, then if you have a child process, then you can't really share. Okay, so what you need to do in this case is to create a brand new page. I'm going to allocate a new page in physical memory, copy the entire thing over here from here, right? So this entire 4 kilobytes, you're going to copy everything over here. So now d is going to be still equal to 5, right? Because this page is going to be exactly the same as the page sitting on the disk. Okay? And then the next thing that you do is that you go over here and you change this pointer. Instead of pointing it to this page, you point it to this page. All right? And then you let this process write to that particular memory location. Okay? And now when this process tries to write d equal to 7, d is going to be an address in the virtual address space. It's going to access this particular memory location, go through this page table, and now this guy is going to point to this page instead of the other page. So when this guy set this d equal to 7, it's going to set d equal to 7 in its own private copy of this memory page. All right, so in the beginning, when this, let me go over this again, right? In the beginning, when you start off the process, you map the entire file on the disk into memory, okay? But in that case, you want to make sure that, in that case, this page will look exactly the same as on the disk, okay? But when you try to write to it for the first time, you want to make a copy, and then you write to the copy, okay? So this particular principle is called copy on write, or COW, okay? Copy on write, okay? So over here, so how do you really make this work? Copy on write, right? So when I try to write to this page, well, if this particular page protection is read-write, it will just write to this page. Okay, so the operating system actually have to play this trick of setting this access, bit for this page to be read-only. Okay, so this way, when you try to write to this particular page, you're going to get a fault and then you're going to trap into the operating system so the operating system can fix it. Okay, so you try to write to a page that's not, writable. Okay, so that's a fault. It's like a segmentation fault, access violation. You trap into the kernel. Kernel look at this and says, I know what you're trying to do. You're trying to, perform copy on write. Okay, so therefore, the kernel would do that for you by making a copy, by allocating a page in memory, copy this page over, fix the page table, and restart that particular operation. Okay, so there are these instructions, that cause a trap into the operating system. Some of these instructions are restartable, and some of them are not. Okay, so for example, if you execute a trap machine instruction, you trap into the kernel, and that one, the kernel will just provide a service for you. So the trap instruction, when you return back into the user space, that instruction will not be restarted. Okay, but if you try to reference a memory location and cause a violation, cause a segmentation fault, in that case, that particular memory reference is going to get restarted. Okay, so in this case, you try to write to this memory location corresponding to D, you try to set it to 7, you will trap into the kernel. When the kernel fixes it, it will come back to user space and you will restart the operation. All right, and this time when you get restarted, this pointer better point to this page, and now this guy's access better be read and write, so you can just, read and write that particular memory location and set D equal to 7. Okay, so this is also very useful when you have a child process that tries to do the same thing. The child process in the beginning, when it first got started, this one is also read-only because it's pointing to a page that's identical to what's on the disk. All right, so as soon as the child process also try to write it for the first time, okay, it's going to access this memory location for D, right? This guy's saying D is equal to 15. Okay, so it try to set that memory location. You're going to get a segmentation fault. You trap into the kernel create another page, copy this page onto this thing, fix this pointer to point to this one, and return back into the user process. The user process will restart that operation, and then this time it will map into this memory page. So at this point, D is still equal to the original 5. Now they can change it to 15, so now D is equal to 15. Okay, so now does the parent and the child process, do they really write into the same shared page? No, right? So now the parent and process are protected from each other. They cannot corrupt global data structure by modifying global variables. Okay, so this copy on write is a very important operating system principle that can be used over here, so that you can achieve efficiency, so that the parent and child process can share an address space to start with, but later on when they try to modify data, they will get their own copy. All right, so this is an important thing, and I guess it's sort of summarized in this page. Copy on write. All right, and when you create, and so also over here, it sort of point out that there's a special treatment that actually treat the data segment and the BSS segment slightly differently. Okay, so again, inside on the disk, right, you have prog over here. Okay, you have text, data, BSS. Okay, so we might want to keep the pages for data segments and BSS separate. Okay, because what happens is that the BSS segment, they can, what should that page be initialized to? Right, BSS contain uninitialized global variable. Okay, what should they be initialized to? Well, garbage or whatever it is, doesn't really matter. Okay, so for a system like Linux, Linux actually try to be nice. They say, well, we're going to initialize them all to 0. Okay, so you're going to, I don't know if you find out that already on Solaris, on Nunkey, that they don't really initialize any of the data pages. So if you get a fresh data page, you're going to get garbage on it. Okay, Linux actually try to be nice. So in that case, what happened is that inside memory, okay, the data segment is going to go to their own page, and the BSS segment is going to go to this page that's full of zeros. Okay, so the data segment is going to get put into memory, and they will be initialized using code inside the program, to set these variables. Okay, over here, it's a page of 0. Some operating system will call these guys, especially in Unix, their kernel assignment. These are called anonymous objects. Okay, yeah. So these anonymous objects, they are. Let me see. Oh, sorry. I guess the data segment, this also goes to anonymous objects. So there are two types of anonymous object. One of them is that, they start with some values, okay, but they are also set up so that you can do copy on write, okay, and the other kind of anonymous objects are pages of 0, so you can use that to initialize BSS segments, okay. So this guy, the anonymous object works the same way as the way that I just described, so you can have, multiple processes, they all point to the anonymous object in the beginning, and when you try to write to it for the first time, you get your own copy. Okay, when you try to write to it for the first time, okay, then you get your own copy, and then you write to the copy. All right? So the anonymous object is actually used all over the place in the operating system, for copy and write. Okay? These other pages that are related to the code, okay, they are read-only pages, and they always stay read-only, so they are really not anonymous in the sense that these pages actually have names associated with it, right? They're not anonymous because they actually point back to the disk where they came from. Okay, these other pages, they can't really point back to the disk. Well, actually, this one can. This guy can actually point back to the disk, but the pages of 0, they really have no place to point to. Okay, so these other objects are slightly different. All right, so these are for copy on write. Okay, and if a bunch of processes share a single file, okay, you can actually have different processes. They purposely they want to share a file. Right? For example, if you have a database system, the database system, you want to use them, you want to take out a large chunk of the disk to use that as a database file, then many processes are going to write to it. Okay, so in that case, that particular file sitting on disk is shared. Okay, so if they are shared, we can actually go back to this picture. Okay, so let's say that this is not a data, this is not the data segment. Okay, it's some sort of a shared file. Okay, if it's a shared file, is it okay for them to share the same page? Right, this page reflects what's on the database disk. So here's the database. There are pages all over the place. This one mapped to this page on the database. All right, so since all these processes are supposed to see the same thing on the disk, therefore they can share the same page in memory. Okay, so these pages are not copy on write, even though they are associated with data, with data. Okay, so what you can do is that you can actually say that, here is a big file. I want to map the entire file into memory and want to map them in a way that's shared by all the processes. Okay, so in that case, all these processes that are used in this file, they will have the corresponding page table entry over here to say that they are both rewrite. They're not doing copy on write, right? If they're doing copy on write, they will set it to read first, and when they write to it, they will change to rewrite. Okay, but in this case, if they want to share the same file, then they will say read and write. Then all the read and write, they will all go to the same page. Okay, so now if the processes want to write on the same location, is that okay? I mean, doesn't sound right? But they want to share the same file, which means that, yeah, if one write to it, the other one write on top of it, then the other one should see, that data has been changed. Okay, so once we declare this particular page, so that's another name that's to go with it. Inside this page table, there's another column. Okay, this column is private or shared. Okay, if this one says they are shared, well, then they can step on each other's toes. That's perfectly fine, because it's as if they're writing to the file, writing over each other. Okay, so Unix is very different from Windows in that sense that, if you want to write, to the same file, go ahead and do it. Okay, you can actually, I don't know if you noticed that, you can have two editors editing the same file. Okay, and then one open it, change it. The other one has already had the file open, and you make some more changes, then you write to it. That's going to be allowed. Okay, on Windows, Windows operating system, they actually provide lockings in that particular case. So if you try to open a file and then you want to open another, open the same file using a different application, it will say this file is already in use. Okay, so it's an operating system choice whether they implement something like that or not. Okay, so Unix and Unix, they let you, share file like this. All right. Okay, so this one is different from copy on write. If you want to share explicitly, you can also do that. Okay, but the basic mechanism is called memory map file. Is that you map, a part of the file onto memory so that when you try to modify data in memory, it's like modify data on file. Okay? All right, so mapping this file into address space, okay, there's actually a system called mmap that allows you to do that. Okay, so when you map, part of a file into the address space, so when you modify things in memory, it's as if you modify things in file. This is referred as doing block I/O. Okay, because you are making you're doing I/O operation a block at a time, right? You can map 4 kilobytes from the disk into memory, modify anything you want, and then in the end, when you close the file, everything will be written back to disk. Okay, so in that case, you're not doing read and write of that particular file. You map it into memory and just modify whatever you want. Okay, so it's a really convenient way to sort of instead of operating on file, which that you have to go through that sequential abstraction. But now you can just you can access the file in any way you want. Okay, so this is fairly convenient. But as it turns out that this is really not the abstraction in general we want to provide with the user. Okay, the user, we talk about, the file system interface is open, read, and write, and close. Okay, those things are sequential I/O, right? Because if you read 100 bytes and you try to read again, it remember that you have read 100 bytes, so it'll continue from that. Okay, so the normal way that we do read and write, that's called sequential I/O. And the abstraction of the file, it's a stream of bytes, right? Here's byte 0, byte 1, et cetera, all the way to the, to the end. Okay? So this is the usual abstraction. Most application program, like your warm-up number 1, warm-up number 2, you're doing sequential I/O. Okay? We rarely do block I/O. So block I/O is actually for, even though it sounds really convenient to do something like that, okay? But in reality, most of the time, our program, the user application, do sequential I/O. Okay, block I/O is something that more or less the operating system does. Okay, and if you implement some kind of a lower level application like a database management system, you will end up using block I/O. All right, so please keep that in mind. This is what user application normally do. Okay. All right, and also for Unix, what they also try to do is to make every device sort of look like, I/O. Okay, so for example, if you want to read from the keyboard, right, what do? We read from standard in, right? Standard in is connected to the keyboard, so you have to open the keyboard and then do read and write, or you don't really write to the keyboard, you write to the screen. Okay, so usually when you talk to the unit devices, you are doing sequential I/O. Okay, so when you try to read from the keyboard, you can read one character at a time, read one line at a time, whatever the C library provides to you. But you treat these things as sequential I/O, so the abstraction is a stream of bytes and not a block of memory. All right? Okay, all right. So one of the things that we try to do with Unix, system call API is that we really don't want to change them. Okay, we try to sort of stick to what we have, and that's sort of reflected by open, read, and write. Right, those functions are, as it turns out, they are very, very nicely designed. Okay, they can be used on files, on devices, on pretty much anything. So even though any kind of a future devices that you invent, most likely, in order for you to interact with that device, you can do, either sequential I/O or block I/O. Okay, you don't really need anything else. Okay, so therefore, for you to do these I/O, all you need is open, read, write, close, and memory map and something like that, and then you're set. Okay, so there's really sort of the philosophy that backward compatibility is a very important issue. Okay, you don't really want to change the system call API. Okay, you want to keep them as as much as the same as possible. So even when you creating new devices and stuff like that, you try to find a way to fit into the current system call model. All right. So that's and that's sort of the Unix. Pretty much all the operating system has that kind of philosophy. And to make it portable, to make the operating system portable, right? Because the hardware does become different. We mentioned that there's this thing that we're really not going to go too much into, and that's called the hardware abstraction layer, right? It's pictured right here. It's between operating system and the hardware. Okay, so even for the same processor, you might have different hardware abstraction layer, depends on your machine configuration. Okay, so every time when you have a new machine or a newly configured machine, all you have to do is to either modify the current hardware abstraction layer or write a new one. Okay, and hopefully you don't have to change the kernel. Okay, the kernel code, all you have to do is to relink with the kernel, and then you have a you have a new machine that's ready to go. Okay, so that's the importance of the hardware abstraction layer, is to provide that that extra layer of abstraction. Okay, so in the operating system, how do we deal with devices? So we're going to briefly talk about this framework for devices. Okay, and remember that our example, our simple operating system, right? The device that we talk to is a terminal. So this is a picture. I don't know if you can see this. This one says Digital Equipment Corp right here, digital, and then VT100. Okay, so this is one of the classic, terminal, right? The screen is, 80 characters across, 24 lines, and it cannot do bitmap graphics. It's only do character, character stuff. And here's the keyboard. Okay, so the keyboard comes with a monitor, and then there's a cable over here that get connected to one of the controller board. Okay, so this is a terminal controller board. Okay, the terminal controller board sit on the bus, right? Here's memory, and here's CPU, etc. Okay, so when you press the key on the keyboard over here, you generate interrupt to the CPU. The CPU use the device driver and try to, read, to talk to the terminal controller board to try to figure out what has been typed, etc. If you want to print something to the screen, you talk to the terminal controller board over here, and this one will send a signal to here to display a character on the screen. All right? So this is VT100. Later on, there's, VT200, 300. I think these days, when you log on to Nunkey, I'm not sure what is the default terminal type. So what happens is that when you're running a terminal program, like in Ubuntu Linux, or when you secure shell to Nunkey, you're going to get something that looks like a terminal. Okay, so that's like a virtual terminal, right? Because it's no longer the physical terminal anymore. Something that looks like this. And that terminal is going to run a terminal emulation mode. Okay, so what it's trying to do is try to emulate this particular, machine. So on Unix login, there's an environment variable called term. Okay, you can actually say echo $term when you get a Unix prompt, and it will tell you what it's trying to emulate. Okay, sometime in the good old days, it will say that it's emulate VT100. Okay, and then you will see VT300, and there VT342 or something like that. So basically, they're trying to emulate, a machine like this. All right, so whenever you run terminal, I guess similar on the Mac OS X, where you have a terminal program, they all doing some sort of a terminal emulation. Okay. All right, so this is even before terminal. There's no screen. There's a piece of paper that get printed out. So that's really old. All right, so we want to be device independent. So when you plug in different devices, new manufacturer is going to come up with new keyboard, new display, new mouse, and stuff like that. We want to be device independent. We also want to make sure that we can discover all these devices. Okay, so some of the devices that get discovered are during boot time. So I'm going to talk about it in the next lecture. When you boot, it does a bunch of device discovery, find out what devices are plugged into your machine, and then make sure the device drivers are installed into your operating system kernel. Okay? In the good old days, all the device driver are pre-configured into the operating system. Okay? So if you have an operating system kernel, so this is good old days, 1970s, 1980s, or something like that. There's actually tons of device driver that are part of the operating system. Okay, so the operating system is sitting in one big, piece of code sitting on disk, and this one is the monolithic operating system. Okay, so in that case, if you want to add a new device, what do you do? Okay, if you want to add a new device, you need a new device driver, right? So the device driver, they can't really exist outside the operating system, so you need to add it into the operating system, which means that you have to recompile the kernel. Okay, so in the good old days, it's really painful to add a new device into the operating system. Okay, you need to recompile the kernel, and you also need to reconfigure the kernel to now be able to recognize when to use this particular device. Okay, so the device discovery was sort of a different kind of game in the good old days. Okay, things have changed, quite a bit. Okay, and these days we sort of mentioned that we're going to use USB, protocol, so that there's only one kind of device that are sitting on the bus, and you use a protocol to try to deal with these devices. To name these devices, there are basically two choices. One is to have some sort of an independent namespace. So if you are, building a not a general purpose operating system, some kind of a specialized operating system, you can do anything you want. Okay, so you might end up using something like this. You have special ways to name every device. Okay, and for that kind of a system, usually you have a limited number of devices that want to be plugged in. Okay, for general purpose operating system, right? Windows probably support, I don't know, tens of thousands of devices, if it's not hundreds of thousands of devices. So how do you really name all these devices? It's going to be really, really messy. Okay, so usually, you sort of name them, as files, so they become part of the file system. So when you go to the file system and then you start, looking into it, you're going to see devices inside the file system. Okay, for Unix, everything is going to be under /dev, and then there's something like, disk 0, disk 1, all that kind of stuff. So every one of these directory entries inside a /dev directory actually correspond to a file. Okay, so how does that really work, right? I mean, So the way that you do this is that you specify the device driver. So every device, you're gonna have this kind of a naming convention, so that every device is identified by some sort of a device number. Okay. So for example, if you go to /dev, you can actually go to /dev /disk 0. Okay, and you can open that file and see what's in it. Okay, if you open that file, you're going to see there's two numbers in it. Okay, so for all the devices, they only have two numbers associated with every device. Okay, the first number is called, so this one might be says 3.7 or something like that. So the first is the major device number. Okay, this one identifies the device driver. Okay, so what happens is that when the operating system gets boots up, it's going to load, all the device driver into the operating system kernel, and they're going to keep track of these device driver using an array. The kernel data structure that they use is just an array of device driver pointers. Okay, so here's an array, and they have many entries. Each one of them point to a device driver. Okay, and remember, device driver. What is a device driver? It's just a collection of function pointers, right? Okay, and the first one is, initialize. Second one is read, and then write. There's interrupt, and then there's wait, or something like that, right? Okay, or start, read, start, write. We'll talk about that already. Okay, so every one of these things point to an array of function pointers, and then this table, the major device number, tell you which index in this table that you're using for that device. Okay, so in a way, we identify devices based on which device driver it uses. Okay, so if your operating system load up 20 devices, well, this array is going to have 20 entries. Okay, and then there's this minor device number telling you that for this device driver, how many devices is it controlling? Okay, if this one's controlling 7 devices, then the minor device number is going to go from 0 to 6. All right, so this is how you, sort of identify these things. Okay, so /dev /this one and this two, these things are, they are marked as special files. Okay, so what happens is that inside every directory, you have to label every directory entries and what kind of directory entry it is. Okay, so you can distinguish between things like regular file, directory, and now we see another thing is, these are called special files. Okay, special files are devices, and if you look into the data inside these special files, you're going to see the major device number and the minor device number. All right. And also, if you do ls minus l /dev /this one or /dev /these two, you will also see the major device number and the minor device number, because the ls command implements how to how to display these special files. All right, they will print their major and minor device number. All right. So here's the picture. Right here is the array, the kernel data structure. That store all the device driver or points to all the device driver, and when this guy will point to is a device driver, and the device driver has the start read, start write, interrupt, and wait, all these kind of functions. Okay, so different kinds of devices might have additional functions. So the general device driver structure it's just, simply an, array of function pointers. All right? Okay, so devices are sort of represented in a very, simple way, because in the end, all you need to do is so if you need to go read a from a particular device, right, what you need to do is that you need to look up the device number, go to the right entry, and then invoke the corresponding function for reading that device. Okay, so in this way, the kernel is become device independent, right, because the kernel doesn't really have to know anything about how to read and write that device. All it needs to know is, which index to use in this table and which function pointer to invoke indirectly for reading and writing that particular device. All right? Okay, and I mentioned this already. In the early days, things are statically configured. Later on, they come with probing the device. So when you boot the kernel, you go to the bus and you say, is this device there? Is that device there? Is that device there? And if you have 10,000, device drivers in the kernel, that will take you a long time to boot. In the good old days, yeah, it does take quite a long time to boot. Okay, and later on, things get improved. And these days, we use, USB, right? And USB is kind of a meta driver. So we just use one driver in the kernel, and that driver can actually go to the USB bus and try to discover all the devices on that bus. Okay? So that protocol is not a dumb, probe and response kind of protocol, right? Probe and response is that you have to say that, it's device number 315 there, and you didn't hear from it, so device 315 is not there. How about 316? How about 317? Right? That's really a dumb way to talk on the bus. Okay? USB is much more, smart. What it will do is that it will broadcast a signal on the bus to say, hey, everybody respond to me. Tell me who you are. Okay? And that's a much better way to manage these devices. Okay? And also, using the USB protocol, you can download a device driver from the device and install that into the operating system dynamically. Okay, so these kind of a dynamic linking, so these are called kernel dynamically loadable kernel modules. Okay, so these device driver can be loaded into the kernel while the kernel is running. Okay, so things, of course, has come a long way. But again, in this class, we sort of, I guess when we do the kernel assignment, we sort of, focus on the, the 6th edition Unix when things are a little simpler. Okay? All right. So, we're not going to get into too much into this. This one has a gray X in the lower, left-hand corner. We'll skip. All right, so that's the basic, quick introduction into devices. Later on, I guess in chapter, I guess what we do is that we'll try to, finish the first part of chapter 4, and then we're going to go into chapter 5, and then we're going to come back to the rest of chapter 4, and then we're going to see the device implementation in a lot more detail. Okay? So for now, we're going to sort of skip ahead. All right. The next part is to look at processes and thread. And again, we are doing a quick introduction. And in chapter 5, we're going to look at more detail. All right. Again, a process, said it many times. I'm going to stress it again, right? It's an abstraction of memory. It holds the address space. So the address space, right, is what the program thinks the memory look like. Okay, 4 gigabytes of address space. It has a collection of other information shared by all the threads, right? It holds all the threads together within that particular process, and it protects. It provides context for switching between threads, and also provide context to keep track of open files, okay, and things like that. All right. As we discussed in Chapter 1, processes-related APIs include fork, exec, wait, and exit. Okay, so again, a very small set of system calls that they don't really get changed much over the years. Okay. All right. So what does the process control block look like? So here's the process control block, right? Okay, and according to the previous page, so by the way, this page is very important. When we look at some of these data structure, when you do the kernel assignment, refer back to this and see if this matches the process control block in the Unix kernel. Okay, so the process control block, it's a data structure inside the kernel, right? It needs to keep the address space. Okay, so therefore inside here there's an address space description. Okay, there's some data structure in there that describe what the address space look like. All right, you're going to use that a lot in kernel 3. In kernel 1, you don't really have to worry about it too much. Okay? There's an open file descriptors, right? We mentioned that, all the file descriptor table, it's a kernel data structure. Well, it's kept track of in the process control block. Okay? So for every process, you have a separate address space. You have a separate array of open file descriptors. Okay? It has a list of threads, right? So the threads are kept in a list. So every thread is in a thread control block. Okay? So this picture sort of implies already that the thread is somehow implemented in the kernel. Okay? So this is more like in Unix, that is like this. So please keep in mind that you can actually implement thread completely in the user space. Okay? If you implement threads completely in the user space, well, then there's no list of threads because the process is the thread, and there's only one of them. Okay? So when you have threads implemented in the kernel, yeah, then inside the kernel, you need to have data structure to represent every thread, and the kernel is keeping track of all these threads. Okay? So in this case, I have a list of threads or a list of thread control blocks. Okay? Finally, the process has a state. Okay? We're going to talk about what kind of state that can have. But the state of the process is stored right here. Okay, for every user process, it can only be in one state. Okay, and again, the process control block, it tells you exactly what state this user process is in if the process is suspended. If the process is running, some of the stuff might be out of whack. All right. Okay, and the gray area says that the process control block has a lot of other stuff, right? Some of the stuff we already see. Right, the terminated, children list, the process ID, the return code, all that kind of stuff, they're all in there. Okay, and maybe there are more stuff in there. Okay, but the basic idea is that, over here, we're going to pay attention to some of these things here. Okay, and then, when you have a list of threads, it's a linked list of thread control blocks. Okay, it's not an array, but a linked list, so you can actually have lots and lots of, threads. Okay. What's inside the thread control block, right? The thread inside the thread control block, every thread has a separate stack pointer. Okay, if the thread is sleeping, then the stack pointer will point to the right place. It will point to the corresponding stack. And what is the top stack frame again? Switch, right? Okay, so this guy is switch, right? Okay, so if the thread is sleeping, then that's what it looks like. If the one is running, then you don't know what the thread, what that picture looks like. The thread control block, you can also save registers. So why do you want to do that? Right? When you suspend the thread, you want to be able to restore the execution, of that thread. So therefore, you need to keep the state of the thread. You need to keep them somewhere. Okay? Some of the stuff are stored in the stack, right? Like EBP and, the return address and stuff like that. But what about all the other registers? Okay? So all the other registers, they also save over here. So when you need to resume execution of this this particular thread, you need to take all these registers, load them into the CPU before that thread continues to run. Okay, so therefore, these registers, you need a place to save them that goes into the thread control block. Okay, the thread also has a state. Okay, so the state, we're going to talk about it very soon, what these states are, and they keep track of the state transition of this thread. Okay, what are the other stuff? Right, stuff we saw before. Thread has thread ID, has return code, etc. All right. Okay, and also has a next pointer, point to the next guy on the list. All right, and the picture over here, right? If you have 3 threads, you have 3 stacks. Okay, every one of them points to a separate stack, and all these stacks are in the same address space maintained in the process control block. All right. All these threads, they share the same data segment, BSS, heap, and the text segment. All right. So, what kind of state can the process be in? Okay. The process states are very simple. It's not very exciting, right? In the beginning, the process doesn't really have a state. It hasn't been created. Okay. Once it's been created, so this guy doesn't really exist, right? It's non-existent. So the process can only be in 2 states. Okay. It's either in the run state or in the zombie state. Okay. So what does it mean to be in the zombie state? That means that the process, one of the threads has invoked the exit system call, and its parent process hasn't called wait yet. Well, the parent process, even the parent process may have called wait, but this guy hasn't returned yet, right? When it responds to a wait system call by the parent process, then, the entire process gets destroyed and it gets out of the zombie state. All right, so this transition is very simple, right? This is exit. Okay, they made that condition, right? And this guy returned to the non-existent state if the parent's weight returns. All right? Okay, not very exciting, right? Process in Unix, they always keep a parent and child relationship between any of the processes. And I mentioned before when we talk about threads, right? Threads, they are a pure relationship. There's no parent and child thread, even though we said, well, the parent thread created the child thread. But once you do that, they become, peers, and any thread can wait for, any other thread to die. Okay? On Unix, you actually keep track of, sort of a strict hierarchy of parent and child processes. Okay, so in this picture, init created this process, login 1 created this process. So, when you log it in, right, you're running the login shell, you can create, you can run a program, put it in the background, run another one, right, so you can run multiple commands in parallel. And then, the init process on the machine will, so maybe this is num key, allow another user to log in, another user to log in, and they all run different commands. Okay, so the process create a process tree. And on Linux, you can run the command pstree, and that will show you the current process tree. Okay, it will show you the entire process tree. Okay, so you know the parent and child relationship. Okay, so what happened when a child dies? Okay, so let's go back to this one, right? When this guy call exit, right? You run a command, the command finishes, call exit. Okay, wrong picture. Okay. So in this case, what if this guy dies? Okay, the user are running two jobs in the background, and the user says exit or quit, right? I guess on the terminal you type Control D, the login will terminate, right? If you have jobs running in the background, they continue to run in the background. Okay, so what you have to do is that these things now become parentless, okay? But the Unix system requires them to have parents. Okay, the rule Unix must follow is that they become the child of the init process. Okay, so in this picture, it's kind of hard to tell. It looks like they belong, they become the, the children, the child process of the grandparents, but turns out that's really not the case. Okay, we can see that what if this guy dies? Okay, if this guy dies, then these two processes becomes the children of the init process. Okay, so when this guy died, which means that somebody called exit, okay, so that's also what part of the exit system call has to deal with in the kernel is to make sure that every process has a parent process. Okay, so in the exit system call over here, you got to make sure that any child process that are still running, they have a new parent. Okay, so in this case, it will connect them so that they become the child process of the init process. Okay, so therefore, in this case, it will look like this. Okay, they don't become the child process of the login process, right? So why is it wrong to make them the child process of the login process? Okay, because remember, login 1, when they try to wait for the child process to die, is going to stay in a loop to call wait. Okay, and when wait return, it expects to see the process ID of one of its children. If you make this guy the child process of login 1, when this guy, return from wait, it's going to get a PID of these guys. Okay, so who are these? I don't know these. I don't know my grandchildren. Okay, so in Unix, they don't know their grandchildren, right? So they don't know what to do with the PID. Okay, so therefore, this guy needs to be, reparent to the init process. Okay, so what does the init process do? Right? The init process, all it does is, okay, this is the code for init process, while true, wait. Okay, the init process actually is the one that initializes, the system, but once it's initialized, it has nothing to do. Okay, all it does is sit in an infinite loop, waiting for all the child processes to die. All right, so in this case, if all the child processes are running, wait blocks and does nothing. As soon as any of the child process dies, then this guy will collect the PID, right? Is it okay to collect this PID? Well, the parent process is dead, right? So nobody cares about this guy's PID. So, it gets collected by the init process right away, and the return code gets thrown away, and you free up the process control block. All right? Okay, a little bit about threads. When you fork a process, so this is kind of a weird problem. if you have this process, this is the parent process, right? Here is the child process. Okay, when you fork a parent process, and this one actually have two threads. Okay, so the previous picture tell you, how to deal with exit, right? So now we're going to talk about how to deal with fork. If this guy have two threads, and then when you fork, does the child process have all the threads in the parent? I mean, we said that when you fork the child process get an exact copy of the parent's address space. Okay, but we didn't really say anything about threads. Right? So actually there are two different kinds of implementation. One is that, you replicate the, so here's the parent address space, right? It has multiple threads. So you have stack 1 and stack 2, one for thread 1 and one for thread 2. Okay? So now when you create, when you do a fork, you make a copy, so you have both stacks in here. Okay? So logically it seems like, this is all you need. Okay? You should have multiple threads. But is it okay to also do something like this? Okay, so the argument is that it's also okay to do something like this, but of course, in your design document of the operating system, you just say that, well, if you call fork, we're only going to keep one thread. Okay, which thread do you keep? Well, the one that just called fork, right? Okay, fork is a system call. It needs to be invoked by a thread, right? So which thread invoke fork? Well, only one of them invoke fork, right? Okay, so when this guy invoke fork, what happened to this other thread? I mean, in a way, it's saying that I don't really care about this other thread because I'm forking a new process. Maybe I will do exec, maybe I'll do other stuff to wipe out the address space. So this guy doesn't really care about the other thread. Is it okay not to care about the other thread? Yes, because, the same programmer wrote all this code, right? They belong to the same process. So these threads, people who write this code, they are aware of each other. So when you do a fork, that means that if you look at the operating system manual, it says when you fork, this thread will be killed. Well, you got to be very careful when you fork. Okay, so therefore it's okay to actually do something like this. Okay, so different operating systems, some operating systems implement something like this, Linux and Unix. Solaris actually implements something like this. Okay, so this is a lot more difficult to implement than this, right? This, when you, do a fork, you kill off all the threads, you free up all the thread control block, you, delete all the stacks associated with other threads, and then, you only have one stack left, and you go from there. All right, so this is certainly, easier to implement. This one, a lot more work. Okay. So what kind of state does a thread go through? Right now we're going to look at the thread lifecycle. It's a lot more exciting. It goes through many different states. So over here, so let's look at this picture. Right, there's something called the running state, which means that the thread is running. Running means that it's running in the CPU. Okay, so it's not that it's so remember, right, in the CPU, I showed a picture last time. In the CPU, there's a queue in front of it. Right, this one called the run queue. Okay. Or in some system, we'll call it the ready queue. Okay? So when a thread is inside the run queue, this thread is in the runnable state. Okay? When it's running in the CPU, then it's in the running state. All right? So clearly, if you only have a single processor, then only one thread can be in the running state. All the other threads has to be in some other states. Okay? And what are the other states? There's the waiting state that it's waiting for something. Okay? It could be waiting for mutex. It could be waiting for, read and write, system calls. Okay? As long as it's blocked, then it's in the waiting state. Okay? So these two guys, they are both waiting, right? In runnable state, they're waiting for the CPU. Okay? So CPU is treated specially. If you're waiting on the CPU, you actually have a different status. If you're waiting for anything else, you're in the waiting state. Okay? Finally, there's a terminated state, right? A thread call, pthread exit, or return from the first procedure. Okay, so the thread goes into the zombie state. Over here it's called a terminated state. Okay, and waiting for another thread to call join, and that's when the thread ceases to exist. All right. So let's look at all these state and transitions. Right, the thread starts in what state? Okay, when the thread first get created, is it running in the CPU? No, right? So when you call pthread create, you create another thread. That thread is not running in the CPU, right? So therefore, it cannot be in the state. Is it in a terminated state? No. Is it waiting for mutex? Is it waiting for IO? No. So it must belong to the state. Okay? So when you create a new thread, and you have to do that in your kernel 1 assignment, when you create a new thread, you got to make sure that it's in the runnable state. Okay. All right. So how do you, so from a runnable thread, a runnable state, you can see that this picture, the thread transition, the state transition diagram for a thread, there's only one arrow out of the state, and it goes from the runnable state to the running state. Okay, so who is responsible for making this thread going into the running state? Okay, the scheduler switches a thread state from runnable to running. Okay, so when this thread is ready to run, right, somebody, who is managing the run queue? Right, this is the CPU, this is the run queue. Okay, this thread started out sitting in the end of the run queue. Eventually, it moved forward. Well, who is moving the thread forward? Right? I mean, in warm up 2, you sort of see who's moving who's moving threads forward, inside, moving packet forward inside the queue. Well, this is very similar, right? You have a scheduler that moves the thread forward. Eventually, when the thread control block is the head of the queue, and now CPU become free, then the scheduler will move this guy from the runnable state to the running state. All right? I mean, in some systems, these actually combine into one state because you know who's running, so you don't really need to distinguish them using a different variable. What about from running state to waiting state, right? Over here, from running state actually can go many places. You can go here, you can go here, you can go, to runnable, you can go here, you can go here. Okay, let's look at all these 3 transitions, right? First, going down here into the waiting state. So you're running in the CPU, right? Your thread is running in the CPU. How does it go to the waiting state? Okay, it's called pthread mutex lock, right? And then it goes into the waiting state. Okay, so it's the code that inside pthread mutex lock, the implementation of pthread mutex lock, make this guy go from running state to the waiting state. Okay, if this guy make a read call, and read is a blocking call in the operating system, right? So it's the read system call that makes this guy go into the running state. Okay, so many of these, so the system call like read and write can also take you from the running state to the waiting state. Okay, and it's inside the implementation of those system call that make this thread wait, make them change state from running to waiting. All right, so in this case, right, the thread goes from the running to the waiting state. So who made it do that? Right, the thread itself does it, right? Nobody else. The scheduler doesn't get involved. The thread itself, called pthread mutex lock, called read or write. So it's on the action of the thread itself that makes this transition from waiting, from running to waiting. Okay. What about this transition from running to runnable? Who's doing that? Right. So if you're running on the CPU, normally a thread wants to use up all the CPU clock. So that's really not nice. Okay, so we set a timer, and the timer, what happens is that when the timer goes off, this this guy will get put back to the run queue. Right. So again, this picture, right? You have the run queue here, you have the CPU here. When this guy's running the CPU, eventually it uses up its quota. The timer expires. This thread get moved back into the beginning of the queue. Okay, so in that case, who's doing this? Well, it's the scheduler that's doing this. Okay, so when the timer interrupt go off, the timer interrupt will invoke the scheduler, and the scheduler will move this job from the running state back into the runnable state and stick it at the back of the run queue. All right, because it used up too much CPU, right? And what about this transition? There's no description, right? We already know, right? This transition is caused by, calling pthread exit, or I mean the same thing, right? When you return from the first procedure, you also call pthread exit. Right, so this transition is done by pthread exit. Okay. Also, the other thing that can happen if you have cancellation, right? One thread cancel, another thread cancel this thread. So this picture actually tells you when can this thread be canceled. Okay. This thread can only be canceled when it's in the running state. Okay. Why is that? Right. If you call pthread cancel, why can't you just kill that? You have thread A killing thread B. Why does thread B has to run again? Because it needs to execute the cleanup routines, right? Okay, it needs to act. So that's why we keep using the term act on cancel, act on cancel. Act on cancel meaning that thread gets to run one more time, okay, and then in that time it will be in the running state, and then it will execute all the cleanup routines. And eventually, when it finishes execute the cleanup routine, what does it do? It calls pthread exit. Okay, and again, pthread exit will take you into the terminated state. All right, so in the implementation of cancellation, that's where we're all going to do all the cleanup. All right, calling the cancellation, calling the cleanup routines, and eventually call pthread exit. All right, so there's no other way to get into terminate state other than from the running state. So the thread will have to eventually run one more time. Okay, so this picture is very important in kernel 1. Okay, it's pretty much that's what you need to implement, when it comes to threads, implement the thread lifecycle. All right, this other arrow going from waiting to runnable. Okay, who is doing this? Okay, so over here, right, you get here by calling pthread mutex lock. Okay, if you get here by doing pthread mutex lock, how do you get there? Right, when somebody called pthread mutex unlock and you are at the head of the mutex queue, then your thread get moved into the run queue. Right, so remember, the mutex, right, has a mutex queue. The CPU has a run queue. Okay, when somebody called pthread mutex unlock, what happened is that the head of right here get moved into the tail of this queue. Okay, that's what pthread mutex lock does, right? It lets one of the thread goes into here. Okay, so it doesn't really take this thread go directly into the synchronization box. That thread doesn't get to execute until it has a CPU. Okay, so therefore pthread mutex unlock, all it does is to move that job or move that thread into the run queue. Okay, eventually when this guy makes it into the CPU, then it will be executed inside the the synchronization box. All right. What if you wait for I/O? Okay, as I mentioned before several times, right? In the I/O completion interrupt, okay, what are the two things that happen in the I/O completion interrupt? Right. Number one is that you start off another I/O. Okay, you start off the next I/O, and number two is you unblock the threads that are waiting for this I/O. Okay, so therefore it's in the I/O interrupt where this thread get unblocked, so to go move, right? So again, here is an I/O queue. This is one I/O device. Okay, there's one queue over here. When you get an interrupt, you take one of the first job over here because that's the job that the first thread that's over here because that's the thread that you're serving. Right, you perform an I/O operation on behalf of this thread. When you're done, right, in the interrupt, you move this job you move this job back, into the run queue. Okay, so in I/O completion interrupt, this guy changed state from waiting to runnable. All right, so these state transitions are very important, especially, when it comes to, implementing, kernel number 1. All right. Okay, so over here, I guess these are some of the stuff I sort of mentioned, right? That pthread exit, delete. So pthread exit, it kills the thread, makes the thread go into the terminated state or the zombie state. Okay. Over here it says, well, we sort of talk about when you go into the zombie state, you still want to keep the PID and you want to, keep the return code, right? What if this thread is detached? It doesn't really need it. Okay. So can pthread exit actually do a complete cleanup of this particular thread? So as it turns out that it really can't do it, because pthread exit, right? It's a C function. C function, in order for it to execute, it needs a stack. If it needs a stack, can it delete its own stack? Well, that's very dangerous. Okay, so therefore, a thread can't really delete its own stack. Okay, so in that case, the thread can't really delete, this thread, even though it's completely terminated, the thread control block, it sort of needs to be kept around. Okay, eventually somebody needs to clean it up. Okay, so that's why normally the recommended procedure is to have another thread join with this thread. If you have, T2 join with T1, then you're running code in T2, right? T2 over here, you're calling pthread join. Okay, pthread join. Okay, so thread number 2 is executing. Can thread number 2 delete the stack of thread number 1? Yes, no problem, right? You can delete, the stack is in the same address space. Just go ahead and delete it. Okay? So in that case, yeah, this can be done. Okay? So a thread really cannot delete its own stack. Okay? So it doesn't really do a complete cleanup. All right. So over here it says, well, so who's going to delete it if you don't join with it? Okay, there are two approaches. One is to have a special Reaper thread. Okay, so in your process, let's say you created two threads, T1 and T2. Okay, in this particular implementation, what you can do is that in the kernel, you actually create a secret thread called the Reaper thread. R is running over here. Okay, what does R do? Well, R called pthread join with these two threads. So even though these two threads says, I want to detach them, which means that nobody can join with them, but in the end, it's the Reaper thread that will join with them. Right? Why does the Reaper thread have to join with them? So that they can delete the thread control block and delete the stack. All right? Another way to do it is that you put these threads when they're dead, when they're in the terminated state, and if they're detached, you put them in a list somewhere. So over here, there's a list that keeps track of the dead threads. Okay? And this list, they get cleaned up once in a while when it's convenient for another thread to do it. Okay? So for example, if this thread dies, it goes onto this list. Okay? And then, thread 2 is doing something, and maybe when it invoke one of the thread library calls, maybe it will check this list and try to free up the stuff over here. Okay, so basically you have to steal some time, in order to do this management business. All right, so that's another way to do it. Okay, so either way. So, the reason you don't want to do it the first way is it's kind of weird that you have an extra thread that are running that's doing this, but eventually somebody has to do the cleanup. Okay, so maybe when this guy is doing pthread mutex lock, then it can actually go there and clean up clean up this list. All right. All right, so that's sort of a quick introduction, until we sort of get into Chapter 5 to look at how things are implemented. We sort of talk about, some of these thread libraries, what's the implication of making, these thread transitions. The next one is going to get an introduction to, a little more detail in, storage management. So the storage management, the usual terminology talking about storage, that there are two places. One is called primary storage. The other one is called secondary storage. And some people might even heard of tertiary storage. Okay, so primary storage is the physical memory. Okay, so you have the bus, you have the memory over here, you have the CPU right here. Okay, and here's the disk controller, right, connect to a disk. Okay, so this is the primary storage, and this is the secondary storage. Where's tertiary storage? Tertiary storage is the backup of the disk, so it could be the internet, could be some tape drive or something like that. Okay, so we are mainly concerned with the primary storage and the secondary storage. Okay, so the idea over here is that we sort of want to provide some easy way to manipulate a file. Okay, we talk about mapping a file into memory. Okay, so one thing that we can do is that if we have a file sitting on disk over here, we can map the entire file into physical memory, and then over here there's going to be sort of, it takes up just as much memory as it's sitting on disk. Okay, so this way, when you write your data to this particular place in memory, it's as if you're writing to the file. So how do you implement this as if it's writing to the file? Okay, what you can do is that you're going to make sure that, every read and write, you don't go directly to the disk anymore. Okay, you just deal with this particular file, the memory map abstraction. Okay, eventually when you close the file, in the close system call, you write this entire content onto disk. Okay, so that's how you implement as if you're writing to the file. Okay, most of the time when you operate on stuff, you can operate, in memory, but when you close the file, that's when it goes to the disk. Okay, what about if the case when your operating system is not stable, you write, this stuff into the memory for 3 hours, and all of a sudden you have a crash. Okay, then it's going to be really, really bad because, what's staying on this is still the original data. Okay, so therefore, once in a while, yeah, you got to copy some stuff onto the disk to make them consistent. Eventually, when you close the file, then that's when you do the final write to the disk. Okay, so this certainly works if the memory is big enough to hold this file. Okay, what if the memory is not big enough? Okay, so as it turns out that you can also play the virtual memory trick to make this workable. Okay, so we're going to talk about what virtual memory trick that you have to do in order to implement this. Okay, so for example, if you try to map 1 gigabyte file into memory, and you only have 256 megabytes of memory. Okay, so what do? Right? So, the obvious thing to do is that you can, divide this stuff into 4 256 megabyte chunks. Okay, you can bring this file into memory one chunk at a time. Okay, so then what you need to do is that you need to keep track of which chunk is actually in the memory. Right, so these 4 chunks, we're going to give them name, right, 0001, 1011. Okay, another way to look at it is that, to address this 1 gigabyte of memory, you need 30 bits of address space. Okay, so we actually use the leading 2 bits over here, these 2 bits, corresponding to, we can call this pages or chunk, right? So these 2-bit address over here, this is actually the chunk address. Okay, so if this one is equal to 00, right, that means that we want to work on this chunk. If this one is equal to 01, that means we want to work on this chunk. If it's equal to 10, we want to work on this chunk. If it's equal to 11, we want to work on this chunk. Okay, so operating system, if they want to implement this virtual memory to map a large file into small memory space, then what it has to do is that it has to, make sure that you're always going to work on the right chunk. Okay, so how does it do that, right? So what happens is that, when it brings stuff into memory, it needs to remember which chunk it has in memory. Okay, so for example, if it brings, sorry, I got the number backwards. This is the first chunk, so this is 00011011. Okay, so if this chunk is the one that are currently in memory, over here inside the operating system, I got to remember that I have chunk 10 in memory. Okay, so now if the user program says I want to access chunk 11, well, what has to happen? Okay, so first of all, over here you have to trap into the operating system. Okay, so in this case, you will also generate a segmentation fault. How do you generate that segmentation fault? Well, you do a comparison of the first 2 bits in the address against this particular address. Okay, so this again, it's a page table operation. In the page table, you have additional information so you can compare this. Okay, if the comparison is equal to false, right, you feed this guy into a comparator. If this guy returns false, that means that the chunk that's inside the memory is not the chunk that you're working with. Okay, at this point, you trap into the operating system. The operating system can say, well, I want to write this entire block out if this block has been modified. Right, because I'm providing the abstraction that, what's in memory is what's on file. So if this guy is not the same as what's on disk, then I need to write to it. Okay, how do I remember that this, this file has been modified? Again, somewhere inside an operating system, I have something called a dirty bit. Okay, it's a single bit. It's equal to 01. Okay, when you bring a chunk in from, from the disk into memory, I'm going to set this bit equal to 0 because it's the same as what's on disk. Every time you modify something over here, I'm going to set this guy to 1. Okay, so when you modify for the first time, this guy is going to be set to 1, set that this block is dirty. So later on, when you try to remove this block, you better copy it back to the disk. You copy it into this region of the disk, 10. Okay, the dirty bit, if you write it to the second time, it's going to be set to 1. Well, it's already 1, so it's okay. You write it to 100 times, it's going to be 1. Okay, so all you need is 1 bit. All right? So in this case, if the comparison is false, you write this back to disk, and then you bring this one in. Now, how do you know which one to bring back in? You use these 2 bits, right? You're in the fault handler, the segmentation fault handler inside the kernel. So then you know that you need to write this guy out, and you bring this back in. Okay? So after this operation is performed, okay, then as you bring this guy in, I guess it goes into the next page. Okay, when you bring this guy back in, you got to set the which equal to 1, 1. Okay, and then dirty is equal to 0. All right, and then you go back to the user process. The user process is going to restart this memory reference, right? Because this memory reference causes segmentation fault. Okay, so it's going to restart that memory reference. And in this case, comparison is going to return true. So therefore, this access is going to be accessed right here. Okay, if this is a write, it will set dirty bit back to 1. If it's a read, it will keep that dirty bit equal to 0. All right, so this is how you deal with mapping a large file into memory. Okay, so it doesn't really have to be a large file. It can actually be a sort of a smaller file. All right, so clearly moving 256 megabytes at a time that's really too slow, right? Because every time when you get a segmentation file, it's going to take you a long time to copy 256 megabytes. Okay, so that's really not going to work very well. Okay, so what you can do is that you can, do this trick a little more. I'm going to divide every chunk into sub-chunks. Okay, we're going to divide every chunk into 4 chunks, right? So now I'm also going to have the flexibility that different chunk can actually go into main memory over here. Okay, so the bottom one over here, the yellow one, is the bottom sub-chunk of every chunk. Okay, so this one can come from 4 places. This guy will be places 0, 0, 0, 1, 1, 0, 1, 1. So this guy needs to remember where it came from, right? So 1, 0, meaning that it's the yellow one coming from here. Okay, the next one, this green one, comes from here. So remember that it comes from 0, 1. The blue one is the third one, right? It says 1, 0, so it comes from this one. And the pink one is 1, 1, it comes from this one. Okay? So now, the first 2 bits in the address is going to tell you which chunk it belongs to. Okay? And the second one is actually going to tell you which sub-chunk, but it's which sub-chunk inside over here, which one to access. Okay? So by comparing, so when you try to access one memory location, right, you're going to use this one to figure out which sub-chunk that you're going to need, and you compare what's stored in here, because now you need, the which used to be only one place, now it needs 4 things. Because every one of these sub-chunks, you need to remember where they come from, right? So you're going to go to the right one and compare that against the first 2 bits. If this one is false, then again you have to do exactly the same thing. Write it out if it's dirty, and then bring back the new one. All right? So I can break it down a little further to 8 to 16 or whatever. Eventually, this one will reduce to the scheme where every little sub-chunk is 4 kilobytes long, and then we have the paging scheme. Okay, so in the paging scheme, this address, the trailing 12 bits, is going to be accessing, data within a page, within 4 kilobytes page, and the rest of it is going to tell you which part of it comes from the disk. All right, so we can actually take this all the way to something that fill up the address space, which is 4 gigabytes long. All right. All right. Okay, so what's important over here is that we'll go back to this picture, right? Now the page table is going to play, additional, magic over here. Okay, so you can use, segmentation file will trap you into the kernel, and then you can perform all these kind of magic. Okay, so this is sort of the main focus of kernel 3, is that you're going to implement this. So basically, you're going to implement, what get put into the page table, so that you can adjust these pointers to point to the right place, to implement copy on write, to implement virtual memory, to implement all these, all these things. They all use the virtual memory, protection, so that all these things work just right. All right. Okay. All right. So. The way that you implement this virtual memory protection scheme is that basically you're going to implement this particular mapping from virtual address to physical address, right, using the page table. Okay, and you also use that to keep track of what your address space looks like. Okay, so in the end, what implements your address space? It's sort of a data structure like that to keep track of the mapping from virtual memory to physical memory. Okay. So inside the kernel, you don't really want to keep track of every mapping from the user page to from the user virtual address to the kernel address, because that will require you to have 1 million entries. Okay, so that's really too much. So what you want to do is you want to put similar stuff together, and you want to manage them in one chunk. Okay, so how do you do that, right? I mean, the obvious things to do is to keep all the similar stuff together. And what things are similar? Well, every page that are all code, well, they're similar. Okay, so what you do is that you can use one data structure to keep track of all the code pages, okay, and use another data structure to keep track of all the data segment, and then you use another data structure to keep track of, well, these are all the same data structure, to keep track of everything in the stack. Okay, so in that case, we have this picture. Over here, this is the process control block, right? We remember that the process control block, one of the entry there says address space description, right? So it points to this thing called the address space, okay? In address space, basically we're keeping track of, so what is the address space? Well, the address space is the memory map. Okay, so when you try to describe how the memory map from the user virtual address to the physical address, well, basically you're describing the address space. Okay, so the address space is equals to memory map. Okay, because you can actually map everything into memory, and then you manage it carefully, and then you have your address space implementation. Okay, so in this example, the address space is going to be a linked list of different regions in your address space. Okay, so in this user process, how many regions does it have? Okay, I have one region for text, right? One region for data. Maybe I have one region for BSS, right? Because these things are different because they're initialized to be 0 and the other one are not. Okay, and then I have one region for stack. Okay, so in this case, one needs to go into this region, right? This region over here, the data structure name that I use is AES region. AES stands for address space. So this is a region inside the address space, right? So address space is like this. This is the address space. They divide into text region, data region, BSS, right? Maybe heap, okay? Maybe multiple stacks, okay? And also, if I want to explicitly call memory map to map a file into my address space, I can also do that, right? So there's going to be memory map file, in my address space. Okay, I'm going to put all these description of these different regions in a linked list, and this is my address space description. Okay, so what has to go into this address space region? Okay, so every address space region is the same data structure, right? So it needs to remember what kind of stuff? The start address of this region, the size of this region, how many bytes it takes, for that region. Okay, access permission, is this region, read, or read-write, things like that. Okay? And I need to keep track of whether it's private or shared. And why do I have to do that? So I can implement copy on write. Okay, so every one of these regions, I have, whether it's shared or private. Okay? If it's shared, that means that, so this one, so if you look at every one of these entries, right, they have, several entries in the page table. Right, page table has 1 million entry, right? Over here, we use this entire thing to represent it. Okay, so that means that, so if you go back to the picture, here's the page table. Okay, it has 1 million entries in them. Right? Several of them belong to the text segment, right? There, a few of them belong to the text segment, and a few of them belong to the data segment, and etc. Okay, so basically in this data structure, over here, this one represents the text segment. So this one is associated with all these pages that are over here. Okay, so can you figure out what is the page number for all these pages over here, right? If this is page 0, page 1, page 2, and at the top is page 1024, because we have 1 million pages, so it's 1024 times 1024, right? That's the last page. Last page minus, that minus 1 is the last page. Okay, so every page you have a page number. So if you remember the start address and the length, you can actually figure out what page number they belong to. Okay, so you don't have to explicitly represent what page number that they're corresponding to in the page table. You can use the start address and the length to figure out which page table entry they correspond to. Okay, so this way, when you try to update entries over here, you can use the data inside the address space region. For example, shared or private, and write it into the corresponding page table entry. You can use the access permission that's stored in the AS region and write it to the corresponding entry in the in the address space. In the page table entry. Okay, but in the operating system doesn't really have to copy it directly, right? If it needs to implement copy on write, then it will do something a little different. Okay, but the basic idea that you start with is copy these values onto this page table entry, but then depends on how you want to, implement copy on write or memory map file, you might, modify them a little bit so that they work correctly. All right, so anytime you get a page fault because you try to access an entry and then there's an error, you trap into the operating system. What does the operating system do? The operating system is going to walk down the address space to decide how to fix the page table so that when it returns back into the user process, when it restarts that memory access, the right thing will happen. Okay, so the operating system is down there doing magic there, shuffle things around, maybe, create more stuff, create more address space region, updating page table entries, and all kinds of stuff to make all these processes work. All right? Okay, so if it's a memory map file, then it points to the corresponding file object. Okay, so over here, this picture, it says that, these objects, so these, these AS regions, they actually contain something called a file object. Okay, which means that these AS regions, they're associated with a file. Okay, so what kind of stuff are associated with a file, right? The text segment, they're associated with a file. Right, so later on, if you decide to, sort of swap out this entire process, okay, if you keep this information around, then you know that later on you can just read memory pages from the disk and then recreate this entire address space for this user process. All right, so this address space, data search is also very important, right? When when you want to suspend the entire process, put the entire process to sleep because you're running too many things, you want to be able to restore them. You want to rebuild the address space. Okay, you want to rebuild this page table, and you want to repopulate the memory with pages that belong to this process. Well, you can do it, if you know where to get data from. Okay, so things that are copied from the text segment, they need to point to the file and need to point to exactly the file location to say that when you need to copy this, repopulate data for the text segment, this is the file you use, and this is the memory location you need to go to, and start reading from there and populate memory with that data. Okay? Can you do it with the data segment? Right? So this data segment, over here, they're corresponding to the unmodified data. So if you're using copy on write, if it's original copy, yeah, you use this pointer to point to the file so that you can also retrieve that from the disk. What's written on the disk in that executable file is the original data for your program. Okay, so therefore, this guy also points to the file object. What about BSS? Okay, so BSS doesn't really need that, right? So BSS, this guy actually points to anonymous object. Okay, so I guess I made a mistake, earlier in the lecture. I said that, for the data region, they also point to anonymous object. So that's wrong. The data region, they point to file object and not anonymous object. Okay, in this case, this guy will point to anonymous object. And what are anonymous objects? They are originally 0, right? They are created, maybe because of copy on write. Okay, so if you modify something to the data, and now this guy will point to anonymous objects. Okay, originally they will point to file object. Once you do copy on write on them, you modify them for the first time, then it will point to anonymous object. Okay, so the data region depends on whether it's modified or not. It will point to either the file object or the anonymous object. Okay, BSS, well, this is actually BSS plus heap, right? Because right above BSS is the heap, so why not put the heap in here as well? Okay, so BSS heap will point to originally anonymous object is a page of 0. Once you modify it, you get another anonymous object that you point to it, so that's just another one. Okay, so all these anonymous objects, right, they will make up memory for the BSS region and the heap region. But what about the stack? The stack doesn't point to disk, right? So therefore, it also points to anonymous object. In the beginning, they all share the same thing. That's all 0. As soon as you write to it for the first time, then you're gonna get, you gotta get a copy of it. Okay, so when does the stack get modified the first time? Well, pretty soon, right? Because as soon as the startup function for your main program gets started, right before it calls main, it needs to build a stack. Okay, so therefore this thing get created, to copy on write pretty much right away. All right, so this picture also shows this other region, right? Over here, we're going to pretend that, this process called mmap, okay, to map some region of the disk onto the address space. So therefore, you're also going to allocate an AS region to remember, what's going on with this region of memory. Okay, so this region of memory start over here. The length is this minus this. This one is the access is read and write. So that means a shared file. And also over here, actually over here it says it's shared, so it's a shared file. Okay? Over here, this guy, the text region says it's shared. So can you share the text region? Can you share the same file for all the programs that are running? Right? If this process is ls on Nunkey, there are many people running ls at the same time. Okay? So all of their text region, they all point to the disk. Okay, point to the same region on the disk, so you only need one copy on the disk, so they can share, so that's why this is shared. Okay, but in this case, this is read-only. Over here it says RX, on some processor, they will actually do this to make that page executable to distinguish them from read-only memory. Okay, but most cases, this one will be, considered only read-only. Okay, this one is the data region, right? It's read-write and it's private. Okay, in order for copy on write to work, initially, if this guy point right here, this guy will be R. Okay, as soon as you write to it for the first time, you're going to allocate an anonymous object to keep track of memory. Then this guy will point here, and then this guy will be rewrite. Okay, so over here, I need to be a little careful about this because inside this AS region, it's a data structure inside the kernel, so they don't really store exactly what's going to the page tables. Okay, the page table for one corresponding page, they need to do the copy on write magic. But over here in this region, you can actually keep it always rewrite. All right, so the operating system needs to be aware that all the pages that are associated with this AS region, okay, it needs to do copy on write. So therefore, initially, they will all set to read only. Once you make a copy, then the corresponding page table entry needs to be changed to rewrite. Right, here's the page table. Okay, in the beginning, this one is read only. Once you write to it for the first time, this guy will point to some other pages. Okay, this guy will not be changed to rewrite, and this page will be managed by this anonymous object. All right, so over here, if it's original data, it get managed by a file object. Otherwise, get managed by anonymous object. So anonymous object, they are another kernel data structure that can be used to keep track of these mapping inside the page tables. Okay, we're going to get a lot more detail into it in kernel in chapter 7. All right, so for BSS, it's read-write, it's copy on write, it's private. For the stack, it's read-write, it's private, it's copy on write. All right? Okay, all right, so this is the stuff that I mentioned. The fault that I'd be calling segmentation fault, okay, if we only implement pages in the kernel, okay, we use 1 million page table entry, and every page is 4 kilobytes long. Then every fault is called a page fault. Okay, so we're going to use the terms of the page fault and segmentation fault sort of interchangeably to mean that the user process executes something, and the page table says, oh, there's a violation. Okay, you're going to trap into the kernel. The kernel is going to examine the address space representation, the memory map, in order to figure out if you should kill this process or not. Okay, if it's a divide by 0, you go in there and say, oh, divide by 0, kill the process. If you access memory location 0, which you're not supposed to, it will kill the process. Okay, otherwise, the kernel will fix what needs to be fixed in memory and then return to user space and restart that memory access. All right, so that's the process that has to go through. Okay, what about, all right. So over here, I guess the slides over here talk about, managing the primary memory. It's actually is a little more complicated. Okay, if you have 100, processes running on, on your machine, how should you allocate physical memory for these 100, processes? Okay, so if I have memory over here, okay, I have 100 processes, right? One thing I can do is I can divide this up into 100 chunks. Okay, and every chunk I can give it to one of the user processes. Okay, so this is about kernel. Not only has to be efficient and stuff like that. Okay, they also have to worry about fairness. Okay, because now if you imagine I have this machine that's running web servers for my customers. Okay, and these are 100 of my customers, right? They all want equal share of the processor, right? Because they don't want other people to get more processing power than them. So when they pay for this processor, they want 1/100th. Everybody wants 1/100th of the processor. Okay, they want 1/100th of the memory. They want 100 of the disk. They want 100 of everything. Okay, if they know that there are other 99 processes running on the same machine. Okay, so how do you make sure that this guy only get what belongs to it? Okay, can you divide this up into 100 shares and that's it? So when one process starting to use too much memory, then it will have to be suspended. Okay, so it turns out that's really not flexible. And also, there are backdoors that these processes can actually, the user process can actually trick the operating system into doing something else. Okay? For example, if one of these user process decide to open up decide to call mmap to map a file into memory, okay, and then it says, I'm willing to share this file. Okay, I'm very nice. I want to share this among all my 100 friends sitting on the same machine. Okay,
the
so
time
now
is
is this
18
file,
o'clock.
should this file be charged to, so that particular file, we're going to start reading that file into memory. They're going to use up some of these memory. Okay, which part of the memory should it use up? Should it use up memory for this process? This process says, no, you can't really charge it completely to me, right? Because I'm sharing it among all my other 99 friends. Okay, so therefore it should be charged to all the other people equally, and then turns out that this is the only process that's using all of them. Okay, so the operating system needs to also protect the user processes from doing tricks like that. Okay, even though you're allowed to share files, but it needs to be fair even when share file are used in that way. Okay, so it just turns out it's a little tricky for operating system to be fair. So one thing that it will do is that, well, maybe the way that you to allocate memory is that if this is the entire memory, okay, every process is going to allocate a small amount of memory to start with, okay, and the rest of it, this is shared memory. Okay, so if you want to run a memory, if you want to use a memory map file, you want to share that file, then the allocation goes into here. Okay, so all your other allocation, you use the shared memory. If you start using it up, then you have to go to use the shared memory, and in that case, you have to compete for it. Okay, so all the 100 user processes, they might all allocate from the shared pool, and if it turns out that one of the processes is really greedy, then you're going to be in trouble. Okay, because you don't want only one process use up all the shared memory while the other 99 processes are using a small amount. Okay, so what it's trying to point out over here is that operating system implementation, other than all the other consideration, you also need to be very fair, and it might be very tricky to be perfectly fair. All right, when we talk about Chapter 7, we're going to, again, get into a little more detail here. Okay, the file system over here. So again, this is sort of towards the end of section 4.1 of the book. To talk about the file system. The file system has many layers. One thing that almost all the operating systems do is try to make the file system try to make the entire file system independent. So what does that mean, right? So on your Linux system, when you probably install Linux, they will ask you what kind of file system you want to use. Okay, the choices that it will give you are ext2, ext3, ext4. You can also have FAT16, FAT32. Some of the system when you configure Linux, they give you all these kind of options. Okay, so I want my operating system, I want my file system to independent of my file system implementation. Okay, so these are different implementation of the same kind of file system. Okay, and FAT16 and FAT32, they're on Windows, but these days Linux can operate on them. Okay, so they're a completely foreign file system, and I want the same operating system kernel to be able to use that. So how do I make my kernel to be independent of the actual implementation of the file system? All right, so my kernel might have only one file system, might have only one file system, okay? But I want my kernel to be, not to care about the actual implementation. All right, so one thing to do this is one level of indirection, the usual trick, okay? So I'm going to divide my file system subsystem into two parts. One is file system independent, okay? And the other one is file system dependent. So this is called the actual file system in Linux. Okay, I guess Windows call it the file system. The other part on Linux and Unix, this is called the virtual file system. Okay, and if you already read the kernel spec, you see that VFS is the name of our second kernel assignment. Okay, the second kernel assignment, you're going to end up implementing VFS. Okay, in Windows, the virtual file system is called IO Manager. Okay, so this part is file system independent, and this part is file system dependent. So how does that work? Okay, so the way that it works is the following. Okay, we'll go back to this picture we talked about, right? Here is user space. Okay, here's kernel space, right? This is actually the file descriptor table per process. So this is actually the kernel space right here. Okay, the file descriptor table inside the kernel for every process, and it points to some shared data structure. Okay, so this is in a particular address space. This is done for a particular user process. Okay, and then these parts shared. Thank you. Okay, so there's a system-wide file system table where all the open files are stored right here. Okay, so what happens is that we talk about inside here, right? Every entry over here record information about reference count, access, whether this file is open for reading or writing, right? Whenever you open a file, it's recorded over here. Did you open it for reading or open for rewrite? Okay, and this one is the cursor position right here. And the last one, last time we talked about is these things are some kind of an inode reference. Okay, it's a reference to inode, right? And every file is represented by inode. Okay, so over here we're going to go into slightly more detail to say that this is the one that implemented right here. This is actually the file object. Okay, the file object we see that in the address space representation that they point to something called a file object. Okay. So over here, the file object points to this, this table of files, okay, or inodes. Okay, the file object over here, it forms a boundary between VFS and the actual file system. All right, so this is the boundary between the virtual file system and the actual file system, which means that, the operating system kernel, all it has to deal with are everything up to here. Okay, it doesn't have to deal with anything above that. Everything beyond that. Beyond that is in the actual file system implementation. So when you try to read a block from the disk, well, that's actual file system. Okay, the actual file system needs to know for this particular file, where does it sit on the disk? Okay, in ext2, they have a different way to figure out where it's on the disk compared to Windows, FAT32. Okay, so for a particular file, right, there's the concept of, file name, a file directory path, and that will map you to an inode number. Okay, but exactly how that inode is implemented, well, that's file system dependent. So that implementation is actually done in the actual file system. Okay, in the virtual file system, they need to understand that there's this thing called inode, but eventually when you call the implementation, well, you need to go through one level in direction to invoke the routines inside the actual file system. Okay, so what kind of routine do you have in the actual file system? Okay, there's the usual stuff, create, read, and write. Okay, you can also, if you implement, things like, remove file, remove, rm. Okay, remove file, they will be part of the implementation. Okay, this implementation is in the virtual file system. It's also in the actual file system. All right, so the remove, there's one version in the virtual file system that needs to eventually invoke the remove in the actual file system. Okay, and there's also a remove. Turns out remove file, remove directory are actually different. So there's a remove file, there's a remove directory. There's also 20 different functions over here which you will get to implement in VFS. Okay, so the idea over here is that at the operating system kernel, they will only deal with the file system independent implementation. Okay, and then this code in the VFS, they will invoke the right ones in the actual file system implementation so that they can know how to look up a file, how to delete something in the actual file system, how to rename something in the file system, etc. All right. So how do you implement this, right? In the previous slide over here, well, again, we use C++ notation. Okay, we say that these actual functions are actually not implemented. So we say virtual function over here. Okay, so actually in virtual function over here, if they are completely not implemented, then they will say equal to 0. Okay, but you can see that in this slide, it doesn't say equal to 0. Okay, that means that this code actually has some implementation over here. Okay, 1 minute left. Okay, so the one that implemented these functions over here at this level is the virtual file system. Okay, and then one level down is going to be the actual file system implementation. Okay, so the bottom line is that we're going to use an array of function pointers to also point to the actual implementation inside the actual file system. all right, using function pointers. So the virtual file system is going to indirectly invoke these functions in the actual file system in order to, to locate stuff, on the actual disk. All right, last slide. So this is about file system cache, and this is sort of a preview of chapter 6, that the file system actually cache a lot of information from the disk so that the operating system can be implemented efficiently. Okay, and this is called a file system cache, and they are usually implemented using a hash function. All right, when we go into chapter 6, we're going to see a lot more detail. All right, so we're done with chapter 4, and this afternoon I will record an extra lecture starting with the kernel project. All right.
It's been CS402 on Wednesday, June 18th, 2014.